So in this section, we're going to talk about the singular value decomposition. So basically, we know that there are some matrices that we cannot diagonalize, but if you do the singular value decomposition, well, any n by n matrix can be factored as like a QD times P inverse. And we call that as the singular value decomposition. And there are several applications to this in our real life. So let us first see when A is a symmetric matrix. So if a matrix is a symmetric matrix, and lambda be an eigenvalue of A, and x be an eigenvector corresponds to lambda with its magnitude equals to 1, then the magnitude of A times x equals to, well, by the definition of the eigenvector, we have this. Or if you factor out this scalar, then we can tell the absolute value of lambda times x, but the magnitude of x equals to 1, so eventually you will get the absolute value of lambda. So absolute value of lambda measures how much A stretches or shrink certain vectors. And if you set lambda 1 to be the largest eigenvalue of A, then the eigenvector corresponding to lambda 1 measures the direction where A stretches the most. So let us see that with the following example. So suppose that A is given by this 2 by 3 matrix. So it's a linear transformation from R3 to R2. And we want to find the unit vector x where the magnitude of AX is maximized. And we are going to compute the maximum length. So what's going to be happening is like we have the vector in R3 with its magnitude x equals to 1. So in other words, the domain or the original space is kind of the surface of the sphere. And if you multiply this by A, then this will eventually give you some 2D object, something like this. And we're going to find the vector x such that AX, the magnitude of AX, becomes the largest. So there are several things that you can observe. So if the magnitude of AX is maximized, then that is equivalent to have the square of this magnitude is maximized. So this quantity is maximized at the same x as the magnitude of AX. And also we can actually calculate the magnitude squared of AX by changing this to dot product. So this is the same as AX dotted with AX. Or if you switch this to the matrix product, then this gives you AX transpose times AX. Or in other words, we have X transpose times A transpose AX. So now it looks like a quadratic form given by A transpose times A. And if you look at this matrix, then we can tell that A transpose times A is a square matrix. And what is better is, it is in fact a symmetric matrix. So this is because, like if you take the transpose to A transpose A, then this gives you A transpose times A transpose to transpose, or this equals to A transpose times A. So the problem becomes, we want to maximize the quadratic form, which is given by X transpose, A transpose times A times X, subjected to the constraint given by the magnitude of X equals to 1. So from the previous section, we know that the answer, the max value, is the maximum of the eigenvalue of the given matrix. So it is the maximum of eigenvalues of A transpose times A, and that happens when X is a unit eigenvector corresponding to your largest eigenvalue. So if you calculate A transpose times A, then this gives you, so A was given by 4, 11, and 14, 8, 7, and negative 2. So the transpose matrix of this one should be 4, 11, and 14, and 8, 7, and negative 2. And if you calculate this, then you will get 80, 100, and 40, 100, 170, 140, and 40, and 140, and 200. Now, we can calculate the eigenvalues and eigenvectors for this matrix because it is 3 by 3 square matrix. So, if you calculate the eigenvalues, then we get lambda 1 equals to 360, and lambda 2 equals to 90, and lambda 3 equals to 0. And the corresponding unit eigenvectors are 1/3, 2/3, and 2/3. And V2 equals to negative 2/3, negative 1/3, 2/3, and V3 equals to 2/3, negative 2/3, and 1/3. So we can tell that this one should give us the maximum value because lambda 1 is the biggest eigenvalue. So AV1 is the point furthest from the origin. And if you calculate A times V1, then this gives you 4, 11, and 14, 8, 7, and negative 2. And you multiply this to 1/3, 2/3, and 2/3. And this equals to, well, I guess 18 and 6. So the magnitude of AV1 is the same as the square root of 18 squared plus 6 squared. Or this is the same as the square root of 360. And that gives you 6 square root of 10. And in fact, you can observe that this number is the same as the eigenvalue, lambda 1. And that is because this quantity is the same as the square root of AV1, the magnitude of AV1 squared. And this is the same as the square root of the quadratic form. So like V1 transpose A V1. But this is the same as the square root of lambda 1. So we basically call this quantity as the singular value. So in general, if A is n by n matrix, then A transpose times A is symmetric, and therefore it can be orthogonally diagonalized. So let's say V1 through Vn is an orthonormal basis for Rn that corresponds to the eigenvalues lambda 1 to lambda n. Then the magnitude of A times Vi squared is the same as AVI transpose times AVI, or this equals to Vi transpose A transpose times AVI. But if you make the parenthesis over here, then by the definition of the eigenvalues and eigenvectors, we have Vi transpose times lambda times Vi. Then because VI's are eigenvectors for A transpose times A, we get VI transpose lambda sub I times VI. Or if you factor out lambda sub I, then this gives you VI transpose times VI. Or this equals to lambda sub I times the magnitude of VI squared. But because VI's are unit vectors, we get lambda sub I as the answer. So because the left-hand side, the magnitude of AVI squared is always non-negative, so as lambda sub I. So we can rearrange all the eigenvalues as lambda 1 is the greatest one, and lambda 2 is the second most one, and so on till lambda n, but all the eigenvalues are positive. So the singular values of A are the square roots of the eigenvalues of A transpose A, and we denote that as sigma 1 through sigma n, where sigma i's are given by the square root of lambda I. So basically, if you compare this with the above observation here, that you just took the square root for the both sides, so sigma I corresponds to the magnitude of A times Vi. So let us find the singular values of the previous example. So basically, we're gonna use this example to find the algorithm of the singular value decomposition. So basically we had A transpose times A equals to 80, 100, and 40, 100, and 170, 140, 40, and 140, and 220, where we had lambda 1 equals to 360, lambda 2 equals to 90, lambda 3 equals to 0. So from here, we got sigma 1, the first singular value equals to the square root of 360, where this equals to 6 square root of 10, and lambda 2 equals to the square root of 90, where this equals to 3 square root of 10, and the third one equals to 0. Now, for non-zero singular values, we had the corresponding eigenvectors v1 and v2. So v1 was given by 1/3, 2/3, and 2/3. And v2 was given by negative 2/3, negative 1/3, and 2/3. And for eigenvectors for non-zero singular values, we can observe one interesting fact. So if you calculate a v1, then this gives you 18 and 6. And a v2 gives you 3 and negative 9. And if you calculate the dot product of these two vectors, then AV1 dotted with AV2 equals to 3 times 18 plus 6 times negative 9. That equals to 54 minus 54, which is simply 0. So we get AV1 and AV2s are orthogonal each other. So let's say we want to Vn be orthonormal basis for Rn of eigenvectors of A transpose A with corresponding eigenvalues lambda 1 through lambda n, and we know that they are all positive. And suppose that A has R number of non-zero singular values, then the set AV1 through AVR, so there's a typo here. This one has to be AV sub R. Then this set is an orthogonal basis for the column space of A. And if that is a basis, then you can tell that the rank of A equals to R. So singular values also detect the number of basis vectors of column space of A. Now, we're ready to do the singular value decomposition. So suppose that A is an n by n matrix with rank equals to R. Then we can decompose A into U sigma V transpose, where U is n by m orthogonal matrix, and sigma, which is n by n matrix, given by D000, where D is given by the matrix of the singular values, so it's given by sigma 1, sigma 2, and so on until sigma r, and the rest are zeros. So basically, this means that the sigma is a matrix such that we have like sigma 1, sigma 2, and sigma r as a partition matrix, and the rest are zeros. And for V, V is an n by n orthogonal matrix. So let us see how we can do this kind of factorization by looking at our favorite example. First of all, what you want to do is we first find eigenvalues and unit eigenvectors for A transpose A. So we know that lambda 1 equals to 360, lambda 2 is 60, and lambda 3 equals to 0. And V1 is given by 1/3, 2/3, and 2/3. And V2 is given by negative 2/3, negative 1/3, and 2/3. And V3 is given by 2/3, and negative 2/3, and 1/3. And once you find the eigenvalues and eigenvectors, then we can set up V and sigma. So we already know that V1 and V2 and V3s are orthonormal eigenvectors because A transpose A is a symmetric matrix. So we build V by using V1, V2, V3 as these column vectors. So we get V equals to 1/3, 2/3, and 2/3, and negative 2/3, negative 1/3, and 2/3, and 2/3, negative 2/3, 1/3, and sigma that consists of singular values. So basically, if A is n by n matrix, then sigma is also an n by n matrix. So in this case, A is given by 2 by 3 matrix. So sigma has to be 2 by 3 as well. And we fill in square root of non-zero eigenvalues to the diagonal entries. So we get 6 square root of 10 and the square root of 60. Oops, there was a typo here. So the second eigenvalue was 90, not 60. So the second singular value is the square root of that one. That equals to 3 square root of 10. And the rest are zeros. And lastly, we build U by using AVIs. So basically, if R is the rank of A, then the first R columns of U is given by the normalized vectors of AV1 through AVR. So in this example, we have two non-zero singular values or two non-zero eigenvalues. So we have to pick V1 and V2, and we'll normalize AV1 and AV2. So basically what I mean is, if you calculate AV1, then this gives you 18 and 6. So the first column of U equals to AV1 divided by its magnitude. So this equals to, so we already know the magnitude of AVI is the same as the singular value corresponding to that eigenvector. So it should be 1 over 6 square root of 10 times 18 and 6. Or that equals to 3 over square root of 10 and 1 over square root of 10. Similarly, AV2 equals to 3 and negative 9. So U2 should be the normalized vector of AV2. So you divide that by its magnitude. Then that gives you, so you divide that by singular value, which is 3 square root of 10, and you multiply that to 3 negative 9, or that equals to 1 over square root of 10 and negative 3 over square root of 10. So using these two vectors, we can build U as 3 over square root of 10, 1 over square root of 10, and 1 over square root of 10, and negative 3 over square root of 10. So we can decompose A as U times, so I will quickly copy what we have above, negative 3 square root of 10, and sigma, which is given by 6 square root of 10, 0, 0, 0, 3 square root of 10, and 0, and V transpose, that is given by 1/3, 2/3, and 2/3, negative 2/3, negative 1/3, 2/3, 2/3, and negative 2/3, and 1/3. And this way we can decompose A into U, sigma, and V transpose. And U and V's are orthogonal matrices. So please check by yourself that whether if you calculate U sigma V transpose, then that will restore your original matrix A.